Greetings, everybody, and happy Monday. Welcome back. I hope you guys had a great weekend. I wanted to just give you a quick overview of what's happening this week and early next week. We've got one more section that we're looking at in Chapter 4 before our exam, Section 4.5, which is on substitution, and we're going to be talking about that. We've got today and Wednesday, assuming no crazy snow days or anything, we'll be talking about Section 4.5, and then on Thursday we'll be reviewing for the exam, and the exam will be next week on Monday. That exam is going to be covering Sections 3.7 through 3.9, so the end of Chapter 3, and then everything that we've done in Chapter 4 so far. So we'll do a review of that information on Thursday. And then you've got some problems that are assigned to help you review some of those ideas, and those problems will be due on Monday. But I'll put out an answer key out for those problems, just so you have that there. Okay. All right. Before I answer any homework questions, I just want to do a quick review of fundamental theorem of calculus. So let's recall a few things that we saw. So fundamental theorem of calculus. We had this theorem came in two parts. The first part is important for a couple of different reasons, but it's more important because it gives us a second part. But the first part says if we have a continuous function on a closed interval, again, that's in order to integrate. Right now, we typically assume that we're talking about continuous functions. If we define this new function, which is the area from a to x under the old function, so this is an area function from a to x, okay, underneath the original function, then what this first part of the fundamental theorem of calculus says is that that function, capital F, is continuous. It's actually a continuous function, which kind of should make sense if this function is continuous. Then as we're adding area, that should be continuous. But it's actually differentiable, and the derivative is the original function. How fast this area function changes is directly related. It is the height of the original function. Okay. So one result of this is that all continuous functions have antiderivatives. Okay. This area function is an antiderivative. Okay. So that's an important thing here. My pen's already running out, so let me switch here. Okay, let's go into part 2 now. Part 2, again, we've got a function that's continuous on the closed interval, so it's a similar setup. Okay. So the way that we evaluate the definite integral, the area from a to b, under a function is you simply find an antiderivative and plug in a and plug in b. So f is any antiderivative of little f, and you just take capital F of the upper limit minus capital F of the lower limit. So you find an antiderivative and plug in points. This part of the fundamental theorem of calculus is going to be by far the most useful part. The most useful of these of part of the fundamental theorem of calculus. We're going to find many situations where we want to find an area or something related to an area under a function. And so the key to solving a definite integral, the key to finding an area, is finding an antiderivative. If we can do that, and the first part says all continuous functions have antiderivatives. If we can find an antiderivative, then we can just plug in after that. Does that make sense? Okay. the one homework question that I wanted to do from section 4.4 was number 88. Okay, number 88. This said, let's let, oops, get this right. Capital F of x is the area from negative x to x under t cubed. Okay, let me just draw this for a second so we can actually anticipate the answer. So if this is x cubed or t cubed, and we're going from negative x to x underneath this function, one of the things that you'll notice is that we have the same area on the left and the right, except the left area is negative and the right area is positive. So the answer here should actually be 0. We're going to need to do some work to find that, but the answer here should actually be 0. Now, one of the things that I pointed out before is that in order to differentiate this, you have to have a constant down here on the bottom in order to use the fundamental theorem of calculus part 1 and just do a derivative. Okay, a constant down on the bottom doesn't matter, but it can't be a variable down there. And in this case, we do have a variable down here. So the hint that I gave you before, and I think I worked through a problem where this happened, is that you have to split the integral from like negative x to x. We're going to go from negative x to 0, and then from 0 to x. So this part now that's sitting over here, we can take the derivative of. When we take the derivative, you just take x and stick it in there, and the derivative is x cubed. Okay? This part we can differentiate. This part we can't yet, because the constant has to be on the bottom. So first we have to flip this. And when we flip it, what happens? It's not quite equal. We have to, when we flip things, we get a minus sign. Okay, so this is now our function. And now to differentiate it, for this second part, like I said, I just have constant to x of a function, so the derivative there is just x cubed. That second part is easy. For the first part, I'm going to keep this negative here, and I have to use a different color here. Because this is an x, it's negative x, I actually have an outer function, which is the area from 0 to x, and then I have an inner function where I plug negative x in there. So what I have to do is, in order to do this problem, is I have to differentiate the outer. The derivative of that integral function is just x cubed. So I have to differentiate the outer. That's the derivative of the outer. I have to plug in the inner, and I have to multiply by the derivative of the inner. Does that make sense? So I've got an outer and an inner function here because that's not x, it's something else. The inner function is negative x, and the outer function is everything else. So the derivative of the outer function is just x cubed. That's what we did over here. So I just write parentheses cubed, and then I plug in my inner derivative of the inner. So simplifying, I've got a negative times a negative. These go away, and then negative x cubed is just negative x cubed. And those cancel each other, and I end up getting 0, which is what we anticipated. Okay? Make sense? Okay. So what I'd like you to do now, we're going to enter into a new section. There's a couple things I want to say, but the first thing I want you to do is take out that sheet that I gave you that had derivatives, all our derivative rules on one side of the sheet, and then when you flipped it over, it has all the antiderivative rules kind of flipped around on the other side. So go ahead and pull that out. So So one of the things I want you to realize from the fundamental theorem of calculus is that the key to solving definite integrals, the key to doing derivatives, is finding antiderivatives. The key to doing integrals, I might not have said that right, the key to doing integrals is finding antiderivatives. Okay, if I want to evaluate an area, I have to find an antiderivative. So our methods of finding antiderivatives become really, really, really important. Now on that sheet, we had kinds of functions when we talked about derivatives, and then we had function combinations. Right? Okay. And all of our derivative rules we could reverse to get integral rules. Okay, so we were able to reverse, for instance, we had a derivative rule that said the derivative of tangent was secant squared, so that gave us an integral rule that the antiderivative of secant squared is tangent. Now we have to you have to get in your brain, you have to remember that you have to keep adding that plus c on there if there are no limits on there. If there are limits on that, if it's a definite integral, then you do not, by all means, you do not need the plus c. Okay. Now, so we have a lot of these various rules for specific kinds of functions that we know how to antidifferentiate. For the combinations, the only combinations that we have right now are we could undo the constant multiple, and we can undo sums or differences by splitting them off individually. Okay. We do not right now have a method. There were three other rules here that we had when we were talking about derivatives. We had a rule for products, we had a rule for quotients, and we had a rule for composition. Now the product rule and the quotient rule are really kind of the same rule, surprisingly enough. Quotients are products. They're just products involving fractions. So we are going to investigate how to reverse a product rule or something kind of similar to that. We'll investigate that, but we won't do it until we get all the way to Chapter 7. Okay, in Chapter 7, we're actually going to explore a lot of different other methods that we have for finding antiderivatives, because finding antiderivatives, again, is key to being able to solve a definite integral. We have to find that antiderivative in order to be able to plug in. But composition, that one is the one that we're going to focus on with the section that we have here. So let me just give you, when we did this with derivatives, let me just say it this way. We found a bunch of rules for specific functions, and then what allowed us to get really general and be able to take derivatives of all kinds of functions was that we knew if we combined any of those functions in a certain way, we knew how to differentiate them. The challenge that we have with antiderivatives is you have to kind of know where the function came from, what it is that where you're coming from. Let me give you an example before we go on to anything. Okay. Let's find the antiderivative of tangent. Okay. Now we know how to differentiate tangent, but if you look at your rules on that sheet, there is no integral of tangent. Okay? If you know the answer checking that it's the answer is very easy because doing derivatives is very easy. But figuring out that it's the answer can be very, very challenging. So let me show you what I mean here. So it turns out that the answer to this, an antiderivative of tangent, believe it or not, is negative natural log of the absolute value of cosine. Okay? You might think, where in the world did that come from? I'm not going to explain where that came from right now, but what I do want to show you is that that actually works. So let me show you here. Let's differentiate that answer, and I'm going to forget the plus c because the derivative of plus c is just 0. Okay, let's differentiate that and see what happens. So we have a composition here. The inner function, okay, the outer function is natural log, and then the inner function is cosine. So let's differentiate the outer. So the derivative of natural log is just 1 over x. Let's plug in the inner. And then let's multiply by the derivative of the inner. Now the derivative of cosine, it's a co-function, so we're going to get a negative sign there. And if you're tracking here, you'll already notice that the negative times negative gives me a positive sine over cosine. And sine over cosine is tangent. So in fact, this function did differentiate to tangent. But because tangent isn't in my list here, I have to figure out a creative way to find that answer. It's not like I just have a rule for all of these functions, a rule for tangent and a rule for all these things. We have those rules for derivatives, but we don't have all of those rules for antiderivatives. In part because we don't know how to combine things that we do know how to antidifferentiate in order to get more complicated things that we know how to antidifferentiate. We know how to antidifferentiate sine, and we know how to antidifferentiate cosine, but if we don't have an anti-product rule or an anti-quotient rule, we can't do products or quotients of those very easily. Does that make sense? Okay, so something like tangent doesn't have an immediate answer to us. Now, I fed you the answer, and you can check that it's true, but it's a very different thing to find that answer yourself. Okay? So what we're going to be doing over the end of Chapter 4, all the way Chapter 5, Chapter 6, Chapter 7, what we're going to be doing is we're going to be learning how to reverse the product rule and the chain rule. The product rule is going to wait until Chapter 7, but the chain rule, composition, is going to be today. We're going to find other ways, kind of creative ways, to find antiderivatives, creative ways to find something like this. We're going to ask whether we can do this for every continuous function, whether we can always find an answer. And then we'll look at applications of different integrals. And we'll kind of mix these up so we won't be proceeding we won't be doing all of them at once, but we'll kind of do a little bit of, we'll reverse the chain rule today, product rule not until chapter 7, finding other ways to get antiderivatives. That's really also chapter 7. Will these other ways always work? I guess we'll kind of talk about that in chapter 7. And then applications of integrals of areas. That'll be chapter 6. Chapter 5 will be somewhat of a review. It'll be a mixture. I'll explain that a little later. Okay. So our goal today is to figure out how do we reverse the derivative rule for composition. How do we reverse the chain rule? Okay. All right, so what I'm going to do is let's write down what the chain rule was. And then we'll see what it should look like to reverse it, and then we'll see why it's not so simple just to reverse it, okay? All right, so the chain rule before said that if I have a composition f of g and I differentiate, let me see if I can get a better marker here. What I do is I differentiate the outer, plug in the inner, times the derivative of the inner. And what that means is that if I reverse this, in other words, if I have something in this form, I know that the answer is f of g of x. The tricky part is, how do I figure out that something is in that form? So let me give you an example here. So for example, take a second, and what I want you to do is differentiate the function sine of x squared. I want you to just take a minute and differentiate that. Take a second and differentiate that, and then compare. Okay. What you should see is the derivative of the outer is cosine. You plug in the inner, and then multiplied by the derivative of the inner. That should be your answer. Okay? So what this means, if I flip it around, is that if I gave you the integral of cosine of x squared times 2x with a dx at the end, that answer would be sine of x squared. Okay. Now the challenge with trying to reverse the chain rule is I have to have something that's exactly in this form. In other words, I've got a function, and then inside of it is another function, and the derivative of that function is sitting out here. So you see that, for example, right here, x squared, the derivative of x squared is sitting right out there. Do you see how that format is sort of in this perfect, perfect format that allows me to kind of reverse the entire process because it's exactly it exactly looks right. Now, so the question for us is going to be, how do we, when we're faced with an integral that turns out to be in this format, how do we identify that we're actually looking at something where we're going to be reversing the chain rule? Okay. Well, one of the things that told us that we need to do the chain rule originally, when we got to here, when somebody gave me this problem, I saw a composition of two functions. So when we're reversing this, you notice we still see a composition of two functions. So one of the things that I'm going to be looking for when I want to try to use kind of an inverse chain rule is I need to look for composition. The other thing that you're seeing when we did this reversal is that I have something in the integral that's the derivative of the inner function. You see that? The 2x is the derivative of the inner function. So I see the derivative of the inner function sitting there in the integral, and that is a clue to me that there's kind of an inverse chain rule going on, okay? So what we do that's going to help us a lot is we're going to do a substitution, and that's actually going to be the name of this section. So what we're going to do when we have a hint that there's a chain rule, an inverse chain rule going on here, is we're going to make a substitution, and we'll do lots of examples of this. So we're going to do a substitution where we let u equal whatever the inner function is that we're looking at. So in this case, for example, u would equal x squared. So let's take a look at some examples to see how this works, okay? All right. So if we looked at, for example, the integral of x squared plus 1 cubed times 2x dx, okay? So I'm handing you an integral. And this is not, technically I could do this by cubing this out and multiplying the 2x through. I could do that. I'm not that excited about doing that, but it is possible. That is something that I could do. Okay. All right. But one of the things that I notice is that I see a composition. Notice the inner function is x squared plus 1, and it's sitting inside x cubed. And also notice that the derivative of x squared plus 1 is sitting right there. So this thing is actually set up really nicely to kind of be ready for me to kind of reverse a chain rule. So what we're going to do is we're going to let u equal that inner function. Now, in order to substitute everywhere, what I have to do, since there's a dx here, I have to figure out what's called a differential. We talked about this in section 3.9. But the differential is basically the derivative of this variable. So if you remember, there's a couple of different ways to think about this. But if we took the derivative of this function, du over dx would be 2x. And one of the things that we thought about was that I could move, if I think of dx as kind of like a distance, and think of this as a fraction, I can move that over and I get what's called a differential. So du would equal 2x dx. So what I'm going to do in this integral here is everywhere where I see x squared plus 1, I'm going to substitute a u. And then for this 2x dx, I'm going to substitute in this differential du. This is actually one of the reasons why it's super important never to forget the dx, or what the d whatever is at the end of your integral. It's actually very, very important. You cannot leave it off. You can't forget it. It's telling you what is the main variable that you're integrating in your integral. Since we're switching variables here, I have to switch not only the x's, but I have to switch the dx, and that means I have to calculate a differential, which we're going to call it du. Okay. Now notice that my integral is much simpler, and that's actually a sign that we're going the right direction. If your integral is getting simpler, that's a good thing. Okay, I can do u cubed. That's an integral that I can do. That's going to be 1/4 u to the 4th. Okay, that integral is very, very simple to do. And now what I can do is I can just substitute back in for u what u was. U is x squared plus 1 to the 4th. Okay? Now if I have any doubt, what I can do is just differentiate this answer and see what happens. So if I differentiate, what you'll notice is that I get 1/4, and I'm going to do a chain rule here, which is an indication that I was doing the correct thing by reversing the chain rule. I do the derivative of the outer, plug in the inner, times the derivative of the inner, and notice that the 4th and the 4 cancel, and I get exactly what I had in my original integral. Does That make sense? So what we're doing here is we're now reversing. We figured out that there was a chain rule going on here, and we reversed it using what we call substitution. Okay, let's try another example here. So let's do the integral of secant squared x times tangent x plus 3 dx. Okay. Now, you might not necessarily see a composition here, but one of the things that you might notice is that secant squared is the derivative of tangent. Okay, so if we made a substitution that was u equals tangent plus 3, what you would notice is that the derivative, if I look at the differential du, the derivative of tangent is secant squared, but the derivative of 3 is just 0. So my du is secant squared x dx. That is my differential there. So substituting back in, tangent x plus 3 is just going to be my u. And this secant squared x times dx is, all of that is just my du. You see that? So what I end up getting then is the antiderivative of u is going to be u squared over 2. And then substituting back in, for u is tangent x plus 3, so if I substitute that back in, that's what I get. And if we're ever in doubt, again, I can differentiate. If I differentiate, if I go backwards, I'm going to bring down the 2 and the half are going to cancel. Derivative of the outer, plug in the inner, and then the derivative of the inner is going to give me that secant squared. Okay? Let's try another example here. Five cosine of 5x dx. Okay. Do you see a composition here? See a composition happening. Okay? Really, what's going on here when we write cosine of 5x, we mean cosine of parentheses 5x. So because I see a composition there, what I'm going to do is I'm going to let u equal the inner function there. And then the differential du is going to be the derivative of this, which is just 5, times dx. And you'll notice that it's set up exactly that way to help me. Cosine of 5x is just going to become cosine of u, and then the 5 dx becomes du. So now my integral is much simpler, and I can actually do it. The antiderivative of cosine is sine, because the derivative of sine is cosine. And then I'm just going to stick that 5x back in there. Does that make sense? Now, really what we're doing when we do something like substitution is we're not really doing the integral. We're creating an integral that's much simpler. And when we have that integral, we can do, it simplifies the integral to the point where we can do it, and then we kind of unwind our work. You're actually going to see that happen a lot when we eventually get to chapter 7, where we need to kind of make integrals simpler so that we can actually do them. We need to help make better educated guesses about how to do an integral. So whenever you see a composition within an integral, or you see the derivative of something in the integral, chances are that substitution is the technique that you probably want to try to use. Now, one of the things that I want you to see, I want you to think about the fact that what if this 5 hadn't actually been here? What if the 5 wasn't there? Would that have messed us up? Well, that would have made it a little more complicated, but not really. Let's take a look at what would have happened. Okay, I'm going to do the problem without the 5 there. Then the thing about a constant like 5 is that I can pull it in and out of the integral, right? Constants you can pull in and out of the integral. Other things you can't, but constants you can. So it shouldn't really make a difference whether that 5 was there or not. This technique should still work. Now let's see how it would work if we didn't have that 5 there. Okay? So let's try the same technique because I see a composition there. So let's let u equal that 5x, and calculating the differential, du would be 5 dx. Now I don't have a 5 dx, I just have a dx there. So what I'm going to do is pull this 5 to the other side and make that a 1/5 du. What that's going to let me do now is I now have cosine of u, and then dx becomes 1/5 du. And I'm just going to pull that 1/5 out, and now, just like before, this is a very easy integral for me to do. I can just write sine of u and then plug back in. This is sine of 5x. Okay, it's the fact that this 1/5 was actually very easy to pull out of the integral, which is why having that number there or not didn't actually make that big a difference. Okay, so let me explain. Let me give you another example so you can kind of see what I mean here. Okay, let's do the integral of x times x plus 1 to the 5th dx. Okay. Technically, again, you could do a problem like this by multiplying the whole thing out. That's going to be really, really awful. The other thing I could do is I could notice that I have a composition here. And because I have a composition, if I let u equal the inner function, x squared plus 1, du is going to be 2x dx. Now the question is, do you see a 2x dx somewhere? Now I have a dx here, and I have an x, but I don't have a 2x. But that's not a big problem. I can put the 2 over here, and constants we can pull in and out of the integral. So having a constant over there is actually not that big a deal. So what I can do is this part right here becomes u to the 5th, and the x dx becomes 1/2 du. And the 1/2 just comes out, and u to the 5th is definitely something that I can anti-differentiate. So that becomes 1/6 u to the 6th plus my constant. And then substituting back in, there's my answer. Again, if you're not sure, differentiate to check. Okay, so if I don't have that number, if it doesn't look exactly like the derivative, but it's only off by a number, that's okay. All right, let's try another one here. Let's do the integral of x squared cosine of x cubed dx. Okay. So what you'll notice here is that here's a composition. So because I see that composition, let's let u equal the inner function here. And by letting u equal the inner function, if we calculate the differential du, du is just the derivative, 3x squared times dx. I don't see 3x squared there, I just see x squared. So what I'm going to do is bring that 3 to the other side, make it a 1/3. So in my problem here, I now have cosine of u, and then the x squared dx, this part right here, becomes 1/3 du. And I can, again, pull that 1/3 out because it's just a constant. And then the antiderivative of cosine is sine. So this becomes sine of x cubed. 1/3 sine x cubed plus my constant. Right? Now, if it's missing more than just a constant, that becomes a big problem. So let's take that same problem that I just did. I'm going to change it just slightly. I'm going to make it the integral of cosine of x cubed dx. Okay. So because I see, again, a composition here, I would let u equal my inner function, and my differential du would be 3x squared dx. Now the problem is I have a dx here, but I don't have a 3x squared. That is actually going to be a big, big, big problem. The 3 is not a problem, because I can pull constants in and out of fractions. But you could not, for example, here's what I think you might be tempted to do. Put the 3x squared over here, and then substitute in. So I've got cosine of u, and dx becomes 1 over 3x squared du. Now the 3 you could pull out. But notice that I still have this thing sitting in here, and it's not, in order to do the integral, I have to have everything in one variable. I can't have x's and u's all mixed together. You can't do that. Now I could try to solve for u here, but that's going to actually be a mess and make this integral even more complicated than that one. So this technique would not work in this example because I don't have that magic x squared sitting there that I had over here. In fact, this problem is really, really, really hard, believe it or not. There is not a nice antiderivative that we could write down for that, and we'll address that problem a little later. So there are some problems that seem very simple that are actually very, very hard. So the problem has to be cooked up in such a way that you see almost completely, if not fully, the derivative of the inner function sitting here somewhere. If you don't see that, chances are that you can't actually use substitution. You can try it, but it may not end up working out correctly. Okay? Let me give you another example here. So if I saw the integral, let's take that same one up there, of x squared plus 1 to the 5th dx. Again, I see a composition here, a function in a function, so I might let u equal that inner function, and du would be 2x dx. But the fact that I don't have an x sitting out here is actually a big problem to try to substitute this back in. So this technique actually will not work in this example, and the only way that I could do this problem is actually to multiply the entire thing out. That x squared plus 1 times 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 x squared plus 1. Get a long polynomial and then just do the antiderivative that way. It's possible, whereas this one's actually not even possible to be able to do that. So, does that make sense? So in order to do these types of problems, they have to be cooked up in such a way, this sort of reverse chain rule has to be cooked up in such a way that the derivative of that inner function is sitting around somewhere. Okay, let's take another example here. Let's do sine of e to the x times e to the x dx. Okay, again, I see a composition here, sine of e to the x. So if I let u equal the inner function, then my differential du would just be the derivative of the e to the x. And what's the derivative of e to the x? E to the x, that's my favorite function, dx. That is sitting magically right there. That's the problem was cooked up so that it looks like that. So substituting in, I would see sine of e to the x is u, and this thing out here is created to be the du. And now I have an integral that's much, much simpler, and the antiderivative of sine is cosine, but remember, if I differentiate cosine, I get negative sign because it's a cofunction, so I have to compensate for that with a minus sign there. Plus c. And then substituting back in, we're looking at cosine of e dx, negative cosine of e dx. This problem above would actually not be possible if I just had that and did not have that e to the x sitting on the outside like I do here. This problem is actually not possible, and we'll talk about looking at problems and figuring out is it possible or not and that kind of thing. We'll do that when we get to chapter 7. But the only thing I want to point out here is that this really does have to be cooked up in such a way that the derivative of that inner function is sitting there in some form or another. We call that the du, and sometimes you might notice it and you might say, oh, that's the derivative of something else that's in that integral, and that's many times also a clue that you need to do substitution. Okay, so you've got some problems as examples that you can look through. You should have some time today to be able to work on those. If you've finished up the problems from section 4.4, you're welcome to take some time now to take a look at the problems from section 4.5. Again, remember that you're looking for composition, and you want to try to use substitution where you let u equal that inner function. Okay? We'll keep going a little more with substitution on Wednesday, and look at a few harder examples, because sometimes it's really subtle and it's not necessarily clear exactly what's going on. So we'll do that on Wednesday. Have a great day, and I'll see you guys later.